In this video, we'll introduce the idea of inverse functions. Let's look at inverse functions from more of a graphical or table perspective. Then in the next video, we'll be finding inverse functions algebraically. So let's talk for a moment about functions graphically, and then we'll tie in inverse functions. So if I draw a couple pictures, a couple graphs here, we know that for a relation to be a function, it must pass what we call the vertical line test. So if I draw an upward facing parabola, the vertical line test says make sure that you never touch more than one point when you draw vertical lines through the graph. So in this case, you can see this passes the vertical line test, and that means this is a function. So I'm just reminding us of the vertical line test for a moment, and then I'll introduce how that corresponds to inverse functions. Now, similarly, we know if all I did was tip that parabola on its side, now this graph does not pass the vertical line test. So this fails the vertical line test and is not a function. So this is not a function. So just like the vertical line test can tell us when something is or is not a function, we have a horizontal line test to know if a function has an inverse or not. Let's take a peek. I will again draw two different graphs. So let's begin with, how about just a nice linear function? So I'll draw a linear function. And now let's try this idea of running horizontal lines through that graph. So if I place horizontal lines throughout the graph, do I ever touch more than one point on the function at a time? And you can see, I think here, that the answer is no. So I'm going to say that this graph passes the horizontal line test. And for us, that means the function has an inverse. So I think a nice way to start talking about an inverse function is this idea that some functions have them and some don't. Another graph to look at, just to keep making this point a little bit more clear, let's go back to the idea of a parabola. So a parabola on its entire domain actually fails the horizontal line test. So you can see now I'm in trouble because I'm touching more than one point as I draw horizontal lines through the graph. So this example fails the horizontal line test, which means as it sits, it does not have an inverse. Oops, sorry. Does not have an inverse. Now, careful with the way I said that. So I said as it sits, because if you've worked with x squared, I think you may already know the inverse. And so the way we work around the inverse is by restricting the domain. So again, because we're just starting in graphically, let me comment a little bit on that. The parabola that we started with right here did not have an inverse because it failed the horizontal line test. But what if I take that same parabola, but only draw it on a restricted domain? So I only draw half of it. Now, if I run horizontal lines through, it passes. So there are ways to get around the horizontal line test by restricting the domain. So we'll keep that in mind as we press forward. So that's a little bit of a graphical introduction to inverse functions. Another cool thing is we can actually talk a little bit about just building an inverse function from a graph. So let's give ourselves again another graph. I'm going to make it linear because, as we saw, linear functions seem to have inverses just fine. And I'm going to be a little bit more careful as I sketch this one because we're going to need to identify some points. So let's say the function passes through the y-axis at 3, and then from there I'm going to drop by 2 and run left by 1. So I think we'll be able to even determine the equation of this line based on the points that I just plotted. But just in case it's a little unclear because I'm graphing on just No graph paper here. Let me label these points. So this is -1, comma 1, and 0, comma 3. So that's for the function. What's neat about this idea is since we have a function graphed and we can tell it passes the horizontal line test, we could actually find the inverse very quickly. So what I'm going to do is just, again, reiterate those points that we just found for the function, 0, 3, and -1, 1. And what's about to happen is when we graph the inverse function, we literally flip the x's and the y's. So I'm going to introduce good inverse notation. You maybe have seen this before. It's f inverse of x with the little -1 exponent. That's a common notation for an inverse. And then I'll just show in the table what its ordered pairs would be. So if f had the ordered pair 0, 3, f inverse has the ordered pair 3, 0. So the x's and the y's are literally switching places. And if f had the ordered pair -1, 1, f inverse has the ordered pair 1, -1. So let's plot those on our graph, and then we'll connect the points and get the sketch of the inverse. So 3, 0 would be right here. And then we've got 1, -1 right in there. So I'll go ahead and connect those orange dots, and that would be the graph of the inverse function. So orange is the inverse, blue is the function. All right, so I'm graphing, by hand, I'm sketching. The graph is far from perfect, but some of you who are kind of more visually inclined may notice something about the relationship between the graph of f and f inverse, just visually. And it turns out that a function and its inverse are always reflections across the line y equals x. The line y equals x passes through the origin and has a slope of 1. So I'm just going to put that line in as a dashed line to help hopefully make that point a little bit more clear. So if I were to hold a mirror on the dashed red line, I would see the reflection of the blue or orange lines respectively. So they're reflections of each other. So that's just kind of a nice thing. I like that because if I'm graphing an inverse, I have a bit of an intuitive check. So maybe I'll write a quick note about that. Graphically, this is something a lot of people don't actually realize. They just know how to find inverses algebraically. So graphically, f and f inverse are reflections across the line y equals x, which is just that line that cuts right through the origin with a slope of 1. Cool, so we actually just found our first inverse function for today. It's that orange line that we found by flipping the points from the blue line. Nice. So this example actually showed both graphically and kind of through a table how you can build an inverse function, because we understand now that we're just literally switching the x's and the y's. I'm going to end this video by just pulling in actually a practical example. You may be wondering, why are inverse functions useful? It seems like extra information. So I'm going to appeal to something we often learn in more of a science class. And that is, I'll write down the formula and then see if this looks familiar to anybody. Actually, I'm going to write down two formulas. And as I'm writing this, you're probably having some thoughts about the meaning of these formulas. What do C and F stand for? And you probably are saying it's temperature, right? So these are the formulas for converting between Fahrenheit and Celsius, right? This first formula here, if you input Fahrenheit, it outputs Celsius. So from the standpoint of our function machine, this first example inputs the temperature in Fahrenheit. and outputs temperature in degrees Celsius. And then the second formula here on the right, now we're inputting Celsius and we're outputting Fahrenheit. So would you agree that both formulas have their time and place to be useful, right? We do need both. Sometimes we're in degrees Fahrenheit and we need to convert to Celsius, and sometimes the reverse is true. So these two formulas that we have written here are inverses. If this is the first formula, then this second formula is the inverse of the first. And an easy way to tell is that the inputs and outputs are swapped. So it's kind of like saying if I have a function f, we know a little bit about domain and range, right? And then if I compare it to a function f inverse, that function also will have a domain and a range, but it turns out whatever the domain was for the function f, that is equivalent to the range for the function f inverse. So the x's for f become the y's for the inverse. Similarly, the range for the function become the domain of the inverse. So that little connection, maybe jot it down. It's kind of helpful to think about functions and their inverses in that way. I'm just going to take this example one step further and then we will call it quits here. But let's pick on the Celsius and Fahrenheit thing one more time. Y'all might know a couple key points related to this. So let's take this left side of Fahrenheit to Celsius. So we know that water freezes at 32 degrees Fahrenheit, right? You may also know it boils at 212 degrees Fahrenheit. When you push it into the function, it outputs 0 degrees Celsius as the equivalent of 32 degrees Fahrenheit and 100 degrees Celsius as the equivalent of 212 degrees Fahrenheit. Now, without much thought, if we come over to the inverse, we understand that the values are getting swapped, right? So now the 0 and 100 become the inputs, and the 32 and the 212 become the outputs. So here we have the domain of the function becoming the range of the inverse, and then here we have the range of the function becoming the domain of the inverse. So kind of interesting. Hopefully that gets you a little bit more information about inverse functions. Go ahead and check out the next video where we'll practice finding inverse functions when given an equation.